Right, yeah. So we're going to start off today with highlights on quantum gravity and fundamental cosmology, delivered to us by Mairi Sakellariadou.
Good. Well, let me first thank Chris and Nick for the invitation to be here. So the title of these two presentations, which they are breaking into two parts, is about some elements of quantum gravity and fundamental cosmology. So what I will try to do is, first of all,
there. It's just your voice is very soft.
So first of all, I would like to start with the success of the General Relativity of Albert Einstein, and then to highlight why we need to go beyond GR, and therefore why do we need the theory of quantum gravity. Then I will just highlight some of the quantum gravity proposals. I cannot cover all of them, but I would like just to give you some glimpse of some of the quantum gravity proposals that I will then use in order to find predictions for cosmology. And I will discuss some of the remaining open questions in modern cosmology and some kind of unsatisfactory phenomenological models which we have, and we try to find a fundamental kind of justification or a way to find a kind of alternative proposal. Then I will argue that actually cosmology is not only the best, but probably the only way that we have in order to test theories of proposals of quantum gravity. And therefore I will go back to just examine what are the predictions and implications of the quantum gravity proposals that I will highlight today. And I will finish with some kind of critical views for this kind of proposal, some comments, and some personal kind of thoughts about why we still have some important questions and we cannot find the correct quantum gravity kind of theory. So Einstein's theory of general relativity actually gives us, as we all know, the intimate relation between matter and geometry. So matter says to the space-time how it's going to be curved, and then space-time goes back to say to the matter how it's going to behave. So Einstein's theory described the works in space-time. This theory passed all possible tests. The most important was the last one, which was the direct detection of gravitational waves from the merging of two black holes of the order of about 30 solar masses, the 15th of September of 2014, from the two light interferometers. And this merging of the two black holes released the corresponding of about 3 solar mass kind of energy. Now, by now, we have of the order of 100 kind of detection of gravitational waves from collision of compact objects, and we're able to test GR in the strong gravity regime. So up to now, of course, we have to keep in mind that all the data that we have come from our vicinity for a redshift of about 1, but all the data that we have today, they are in complete agreement with predictions of Einstein's theory of general relativity. In other words, we did not find any kind of discrepancy between the propagation of gravitational waves from the speed of light. We have not found extra polarization modes. All the waveforms that we have based on the GR, they're in agreement with the detections that we have. So general relativity is a very successful theory in order to describe the motion of galaxies, clusters of galaxies, black holes, the entire universe. So when you take Einstein's theory, you have the equations of motion, which is the solutions of Einstein's equation in a homogeneous isotropic background, the Friedmann-Lemaitre-Robertson-Walker kind of universe. So we have there, as you can see, sorry, it's a bit small, the letters in this projection. So we have the Friedmann equation, the evolution equation, and the energy conservation equation. They are not independent through the Bianchi identity. So you have 2 independent equations, 3 unknown, energy density, pressure, and scale factor. So you have to give as well what is the matter content of the universe at a given era. And as you can see, the evolution of the universe depends on the geometry, whether we have a closed and open or a flat universe. Now the point is that as you take these equations and you go to evolve them backwards in time, there is a point which is the beginning of this whole Big Bang kind of cosmological model that took place about 14 billion years back, where all the matter and energy content of the universe we have today is concentrated in a point. So we do not have really a theory that can describe such kind of extreme energy conditions, and this is the kind of singularity that we encounter in the case of the Big Bang. I give you an example. This is the Big Bang. The same thing exists in the case of black holes. So that is where we need to go beyond the classical theory of GR. So I would like just to write down, to just explain which are the singularity theorems. The first is the singularity theorem of Penrose in 1965. It was developed, and in order to just write down the singularity theorem of Penrose, I would like to give two definitions. So what do we call a Cauchy hypersurface? Is an instant of time which is going to give us pretty good initial conditions for the entire space-time. If you want to be more precise, that means that a Cauchy hypersurface is a achronal hypersurface which is met only once by the causal curves. The second definition I would like to give is what we call a closed trapped surface. So let me take the case of the stationary space-time, and then I'm going to take a surface, a two-dimensional surface, from which I'm going to send in and outgoing light. So you have the ingoing. Is there any way that we can make this projection a bit bigger? No. Well, anyway, we have the ingoing and the outgoing. As you can see, probably you cannot see, the outgoing is the blue one, the ingoing is the brown one. So the ingoing is smaller than the outgoing in this sequence of time evolution. If, however, my universe was a contracting space-time, then it's clear that you can see that the area of both the ingoing and the outgoing surfaces can be smaller than the initial one, and this is the definition of the contracting space-time which we can have. So Penrose's theorem states that if the space-time contains a non-compact Cauchy hypersurface and a closed future trapped surface with the definition that they gave before, and if in addition you have for a null 4 vector the convergence condition which I wrote there, which actually in the case of a zero cosmological constant, this is just the strong energy condition, then there are future incomplete null geodesics. So this was the statement by Penrose, which created a lot of discussion within the GR community. And then a few years later came the completion of this theorem by Penrose and Hawking, which says that if you have this convergent relation that I wrote before, and in addition you have these generic conditions that hold for causal vectors, and there are no closed time length curves, and one of these 3 kind of criteria is satisfied, in other words, either you have a closed achronal embedded hypersurface, or a closed trapped surface, or a point with reconvergent light cone, then the result is that the space-time has incomplete causal geodesics. So this is the full kind of the singularity theorem by Hawking and Penrose. And what is the conclusion of that is that if you have some appropriate curvature conditions, then general relativity favors incomplete geodesics versus trapped sets. This might sound a bit weird in the sense that you might have an empty space, and even in an empty space, you have this kind of complete geodesics, and the kind of bizarre arrives because we are usually familiar with the fact that you have an infinite energy density in the point. So if you have empty space, how this could happen. So there is a sequence of observational consequences which one can derive from this kind of singularity theory. The first is the cosmic censorship. So the question is, are the singularities produced in gravitational collapse hidden inside the event horizon of black hole, which is the weaker version of the cosmic censorship? And the other question is, are singularities non-time life, which is the strong cosmic censorship kind of condition. The second one is critical gravitational collapse. If you are able to produce arbitrary small black holes, this implies that you are able to produce arbitrary large curvature, which is going to be visible to observers which are outside. And therefore, you might have the rather extreme limiting case where you have some matter that collapse in order to form a zero mass black hole, which actually gives the existence of a naked singularity. The third one is the Belczynski-Kaladnikov and Lipschitz singularities, which says that actually singularities are space-like, local and oscillatory, and matter does not matter. By that I mean that whatever, for the majority of the types of the matter field, the effect of the matter field, of the dynamics on the, of your geometry is not going to play an important role near the singularity. So the question here is this picture right? And finally, you have the existence of null singularities. So if you assume that both the Belczynski-Kaladnikov-Lipschitz singularity and the null singularities do exist, then the conclusion that you have out of that, if you take an observer which is going to stay together with a compact star that is going to collapse to a black hole, this observer is going to encounter a BKL singularity. If on the other hand you have an observer which is going to fall into the black hole after it has been formed, then this observer is going to encounter a null singularity. So, and then we go, all that is classical, we go to the quantum effects. So, of course, there is this kind of general belief that if you take a quantum version of gravitational theory, then you will be able to cure this pathology of the singularities. In other words, that the singularities by themselves, they just show the situation where the theory breaks down. Actually, the theory is not incorrect. The theory cannot discuss what is going to happen at this extreme kind of conditions. And then the question comes, what can you say about such a situation for inflation and the cosmological constant, which we need for the late time acceleration of the unit? As a matter of fact, inflation is going actually to imply that there is a violation of this convergence condition which I gave before, which is one of the critical ingredients for the singularity theory. And this could possibly imply that it may be that the universe is past geodesically complete. Now, this cannot be the case if the weak energy condition is violated, but we know that inflation, this is not the case because you have quantum fluctuations. However, it has been shown that as long as you have an appropriately average Hubble parameter which is positive, then the violation of the weak energy condition are not enough in order to avoid this kind of past incompleteness that we discussed. There is a critical...
So these quantum fluctuations would still obey the average null-energy condition movement?
Sorry?
Would these fluctuations still obey the average version of the null-energy conditions?
Why you say then the average?
Well, it's a question.
It could be or not. It depends what you. I mean, usually, yeah, you're going to take average of the quantum fluctuations. Once you go to the structure formation, you take quantum fluctuation of the inflaton field.
But do we know that these inequalities are violated in inflation?
Yes. That's the definition of inflation. In order to have inflation, this is violated. Okay. So therefore, why? Because in both the inflation or the existence of the cosmological constant, you have a positive lambda, a positive vacuum energy, which is exactly the opposite of what the conditions of the convergence that I put. You see? So then this turns completely critical to go to re-examine or reformulate the singularity theorems in the existence of a positive cosmological constant, because the basic criterion, which means the cosmological lambda not to be positive, is exactly what you require for the validity of the singularity theorem and why it does not exist in the context of early or late acceleration of the universe. Okay? Okay, so now there is this important kind of, I mean, I don't know if it's important, but it's something that has created quite some discussion, whether you want to quantize gravity or the gravitization, I don't know how to pronounce that, of quantum mechanics. So usually, I don't know whether this is a sociological kind of thing or not, but usually what people try to do, we try to quantize gravity. And then Penrose put forward that it could be an alternative kind of view, that you could try to gravitize quantum mechanics. So this depends, what do you find more important? I mean, there are two pillars of modern kind of physics, general relativity, quantum mechanics. What is the most important one? So, in other words, what is the idea that Penrose put forward is that if you try to see how quantum mechanics should be modified, then you should take into account the laws of GR. In other words, when you go to take a quantum system, you have to find a way that the principle of equivalence must be fully respected in your theory. Now, he has developed a lot to this kind of approach, and what he has found is that there is an expectation that quantum superposition of states, which involve a significant mass displacement, should have a finite lifetime. So then when you go to see what are going to be the scales at which quantum mechanics they will be important, then, of course, you go to the Planck length and to the Planck time, which are of the order of 10 to the minus 35 meters, and 10 to the minus 44 seconds, which are extremely tiny with any other kind of measure that you want to take into account. On the other hand, if you want to go to see what is the quantity which is going to be relevant if you want to gravitize quantum mechanics, there is an energy scale which a priori can be small or bigger because it's the ratio of two small numbers, and therefore in any experiment that you want to adopt, you have to go and see whether this time scale is relevant for the experiment that you have in mind. And there are some experiments, I believe, that Penrose had suggested in order to test this stuff. As far as I know, they have not been fully realized. So, in whatever I'm going to discuss for the approaches of quantum gravity, I'm going to adopt what everybody takes up to now, quantization of gravity and not gravitization of quantum mechanics. But this is an interesting open question. Huh? So there is a variety of different quantum gravity kind of proposals, which in an alphabetical order, so I don't take parts, which is the correct one. I'll tell you what I believe at the end, is ADS CFT, asymptotically safe gravity, causal sets, dynamical triangulations, group field theory, loop quantum gravity and spin forms, matrix tensor models, non-commutative geometry, string theory. That's what I know. There might be more in this zoo of quantum gravity proposals. So what I would like to do now is to highlight for some of them which are the important ingredients. And then in the second part, I'm going to discuss what are the open or unsatisfactory questions that we have in cosmology and how some of these proposals, what I'm going to present today, they try to give an answer. And what are the weak points of this approach. So let me start with the string theory. So now I have not used an alphabetical order in order to discuss them. The basic ingredient of string theory is that the matter consists of one-dimensional objects, the strings. So if you see them with a loop, you can see that there are open strings or closed strings. Here, the red are the open strings, like the photon. The closed strings is like the graviton. So you have that different oscillation of these strings. They correspond to different particles, and then you might have interaction of all these kind of strings, which are going to give to the interactions between matter. Now, there is a string has a tension, which means that you have a fundamental length scale in your theory, which is the string length. And actually, when you go to quantize the string in a flat space-time, what you find is that it lives in more than 4 space-time dimensions. And then the second thing which you realize is that the ground state of a string is a tachyon. So usually you have to get rid of a tachyon. The way that you do that is to invoke supersymmetry. And if you go in superstring theory, then you have that the theory is consistent within 10 space-time dimensions. So the idea then that it is that we have extra dimensions, which actually are very small, like with all this kind of Kaluza-Klein approach, that this point is a sphere, is very small and we cannot see. But the theory is much richer than just this kind of strings, and then it can be the idea of branes. So branes can exist in any dimension you want. One-dimensional branes are strings, zero-dimensional point particles, and so on and so forth. So then that implies that instead of thinking that these extra dimensions are small, the extra dimensions are very big. So you have what is called bulk, within which you have embedded planes of different dimensionality, depends on what is the string theory that you have adopted. And what you have is that all standard particles, they live on the brane, and the graviton lives on the bulk. And that is a reason for why they try to say that the gravitation is a weak force because it propagates in the whole bulk. So this is a picture that you have. And then, of course, you have to take into account that something can happen, like interaction of these branes, so you can get rid of extra dimensions. And one of the three-dimensional space is the universe in which we live. Fine. So I will then discuss.
Yeah. Do you mean only gravity exists in the bulk?
Yes, only gravity in the bulk. So the branes are the.
But you don't mean gravity only exists in the bulk?
No, the gravitons can go also in the bulk, but they are also on the brane. So the brane is the collection of the endpoints of open strings. Okay, that's the definition of the brane. So then we will see how models like that can lead to bouncing universe, to expansion, to whatever. So we'll see what are some of the implications of these models. Now, if you take perturbative string theory, perturbative in the sense that different topologies for the two-dimensional worldsheet correspond to different orbits in a kind of expansion in order of loops, then this theory, the string theory, is equivalent with two-dimensional conformal field theory. So then what you do is, instead of focusing on fields which propagate on your space-time, we actually discuss two-dimensional conformal field theories. Now, if you take non-perturbative string theory, then we will see that space-time is not fundamental, but it is constructed by this holographic dual theory. So holography is a kind of proposal, is an idea that has been put forward, that physics in a given region is going to be described equally well by degrees of freedom which live on the boundary of this region. And then it goes forward the ADS-CFT correspondence, which is also called as the Gauge gravity duality. If you have string theory on a particular space-time, which asymptotically it is like ADS, anti-de-Sitter space-time, and a compact space, then such a theory can be completely described by a conformal field theory which lives at the boundary of infinity. And given that you have this correspondence between the space-time, that means that none of them can be the fundamental one, and therefore, as we will see within the string theory, the space-time that we see in the low energy scale is just an emergent space-time. So you have emergence of space-time here. Now, however, what are, from my point of view, the critical, the negative kind of aspects of this approach is that it does not take into account the curvature of space-time, is something that you put by hand. And then this is the issue, the second one is the issue of the landscape, which is all the values of your fields, which are going to minimize the potential. So within string theory, we have many scalar fields, what we call moduli fields, and then we know that if you change the value of a scalar field, that would correspond to change the value of your potential, and then all the values of your field that minimize your potential is what they are going to create the vacuum state. And then depending whether it is absolute minimum or not, is stable or a metastable kind of vacuum. So by landscape, we call all the values of the field that minimize the potential. And it has been shown that in the case of the string theory, there are at least 10 to the 500 vacuum. Therefore, this, as we will discuss later, it has been put forward like a way to explain the value of the constants in the universe we live, the value of the cosmological constant, which corresponds to the minimum to one of the minimum states of this vacuum, to see that you can have an inflation that lasts forever with a particular initial conditions. From my point of view, this means a lack of predictability of your theory, so you can have whatever you want. So from my point of view, this is more a pathology of the theory that you have. So this is my critical kind of consent with respect to this string theory kind of brain theory kind of approach to quantized gravity. So let us then move to the non-perturbative approach to quantum gravity. So the canonical quantum gravity program is going to take the complete space-time and treat it as a field, and then is going to be an approach of quantizing it without splitting it into a background and a perturbation. So that's why it's called the non-perturbative approach to quantum gravity. So the first thing that one has to do is to go to choose a set of configuration variables and conjugate momenta, which actually they will describe what is the state of your system at a particular point in time. Once you have to that, you have to write down the Hamiltonian, which will give you all the physically possible or motion that you have of your system as a sequence of different curves. And then you will have to quantize the system. So the way that you quantize the system is by taking this configuration and momentum variables and just take them as operators at a Hilbert space. And they are going to obey some kind of commutation relation, which are the corresponding of the classical Poisson kind of relation. And this is going to encode somehow the kind of fuzziness of your system because they obey the Heisenberg uncertainty principle. And then, by writing down the Hamiltonian operator, which is going to act on the quantum states, you could find what will be the dynamical evolution. An example of that is loop quantum gravity. So loop quantum gravity, space-time is made by these loops, by these discrete bits, which means that you cannot chop it in smaller and smaller. I mean, always it's more a kind of sections. At some point, you are going to hit the granularity of your system, which is nothing else than this quantum space, which are the loops. So there is a basic difference between string theory and loop quantum gravity. In the case of string theory, the gravitational field is the background plus the quantum field. In the case of loop quantum gravity, there is no background, okay? Which means that the space is made out of the loops, which means that a state of the space is going to be described by a configuration of loops. So given the space is loops itself, you can never say the location of the net, but you can say the location of the net. And then you take a mini superspace approach, then you just keep some of the symmetries of your theory, and then you make this kind of spin-off of loop quantum gravity, which is loop quantum cosmology. In other words, you take the full theory, which we don't know yet, and you just specialize it in the case of homogeneous isotropic backgrounds, and then you have what is called loop quantum cosmology, which I will discuss in the second part.
Sorry. Would you say that the string field theory is also background dependent?
Background dependent.
But the string field theory, not string theory.
Yeah, it's background dependent. It's not background independent. You have a background. You have the choice of a metric.
Because I guess people in the community, they claim that it would be background independent as well.
But how? What is the proof of that? So, however, I have my however here as well. The matter content of the theory is put by hand. We don't know how to do it. So the matter Hamiltonian is just put by hand. And then, how do you test this theory? By taking the semi-classical limit. And then open another question. What do you mean by semi-classical limit? In order to formulate the semi-classical limit, you need to understand the notion of observers in a quantum gravity context. And the second thing is to construct an effective theory for an observer who can define an appropriate regime for which what is the quantum nature of the space-time is not an essential ingredient. So how do you do that? And here I have some other comments on the semi-classical limit. Now, of course, it's very important to build an effective theory, because that's the only way that you can test the predictions of the theory. Now, quantum gravity, by definition, is the regime at which the Planck length and the Planck mass that are important. Let me take some gravitational effects. For example, I take the formation of black holes. These are going to tell me that the Planck length is a minimal distance and that the geometry is quantized in quanta of the Planck length size. So, the existence of black hole in general relativity implies that there is a maximal bound of the mass of a given, of a size L, which I write it here. I don't know how visible it is done. Now, the quantum effects imply that there are mass fluctuation of the system of the size L of this order. If I assume that in this regime both quantum mechanics and GR are relevant, then the Planck scale is defined as the scale where quantum fluctuations are going to saturate what is the gravitational bound. And from there, if you do this calculation, you can extract what is the Planck mass. In addition, there is an extra kind of dimensionless quantity that you can build. Because in the theory, there exists as well this lambda, the cosmological constant, which actually is a measure of the local mean curvature of the system that you have. And therefore, you can go and you can build another dimensionless quantity in terms of the cosmological constants and the Planck length. Now, in the full quantum gravity theory, the Planck length is the quantity that is going to define the minimal bound on the distances, and the cosmological length is the one that is going to define what is the maximal scale. So usually, there are different limits of quantum gravity that you can take. When h bar goes to 0, which is the classical limit. When the speed of light goes to infinity, which is the Newtonian limit. When g goes to 0, which is the no gravity limit. Or when the cosmological constant goes to 0, which is the flat space-time limit. And this actually implies that the Planck length goes to 0, this dimensionless parameter that I formed from the cosmological constant goes to 0, and that the Planck mass goes to infinity. However, you can have regimes where not all of these limits take place. So there are, in other words, what I'm going to say is there are different semi-classical limits that you can take. So then the predictions of this theory will depend on which particular class of semi-classical limit you have adopted. Now, let me move to group field theory. I just go very brief to all these different approaches, just I would like to highlight what they are. I believe that some of you have been working with some of them, but probably not all of them. I will define almost all the ones that I have been working on, so I know the cosmological consequences. So, group field theories are quantum field theories defined over group manifolds, combinatorially non-local interaction terms, and the whole idea is to take the matrix models that were constructed for two-dimensional gravity and just somehow extend it in higher dimensions. So, there could be a whole variety of group field theories, and the particular type of group field theory that you work in will depend on your choice of the Lie group that is seen like the gauge group of gravity, of the choice of the elementary building blocks, on the choice of the type of the field and the corresponding action, which is going to give the dynamics. As far as I know, the only group field theory that has been studied has a choice of the gauge group of gravity to be the SV2. The elementary building block is the tetrahedron. The type of the field is a complex scalar field, and the action is a quadratic action with some kind of polynomial terms with a different kind of weighting, each of them. And what I will do when I will discuss the consequences of that theory, I will tell you that in order to be able to discuss a successful cosmological model, then I can give some kind of recipe what will be these polynomial terms which I will have in an action that will discuss the dynamics of this group field theory. So the spin-off of that is group field cosmology. So the whole goal here is to be able to find a way in order to model homogeneous, continuum, three-geometrical spaces, which is the space on which we live, and their cosmological evolution by group field theory condensate states. So there is a conjecture. There is good belief to believe that this conjecture is correct, but there is no proof for this conjecture that if there is a phase transition in the group field theory system, which is going to create a condensate phase, and this condensate phase corresponds to a non-perturbative vacuum, which is expressed like all the tetrahedra, the quantum field theory quanta of your theory at the ground state. In other words, this is an approach in order to be able to discuss spatially homogeneous cosmologies. But this conjecture is a conjecture, remains a conjecture. Then I'm going to move on the causal sets. I must tell you that causal sets is an approach to quantum gravity. I personally have not been working, but I just, among the things I have not tested myself, I just picked up this one. It's beautiful, it's very minimalistic, and that's why it's success. Its implications, I believe, are pretty limited. So causal set theory takes the Lorentzian character of the space-time as the important issue, and also the existence of partially ordered sets. So the space of Lorentzian geometry is now replaced by the set of locally finite partially ordered sets, which are called causal sets, and I will give the definition in a moment. And these causal sets are going actually to capture the two important ingredients of the theory, which means the causality and the discreteness. And once you go to take the continuum approximation of that theory, then the order relation on the causal sense corresponds to the space-time causal order, and the cardinality of an order interval corresponds to the space-time volume. So the definition of a causal set is given here. You have a set C with an order relation. This is a causal set. If these conditions are satisfied, the two first, they are cyclic and transitive conditions. They design this posit, this partially ordered set. And the last one, the fact that it's locally finite, it corresponds to the discreteness of the system. So what causal sets tell you is they make this kind of rather radical proposal. Quantum gravity is a quantum theory of causal sets. A continuum space-time is an approximation of an underlying causal set where order corresponds to causal order and the number corresponds to space-time volume. So there is a difference between, let's say, quantum gravity of loops and the causal set in the following way. In the causal set approach, you choose the Lorentzian over Euclidean, you choose the path integral over canonical quantization, and the discreteness over continuum. Such a choice leads to a theory which is called causal sets. On the other hand, if I was choosing the Hamiltonian, the continuum, then I could go to a canonical kind of approach of quantum gravity like loop quantum gravity. So these are the differences which exist here. All of them, they have the discreteness. Now, before I go to the last one, which is non-commutative geometry, I should say that here as well, I have the same pathology of the matter content of the theory, which is put by hand. So, then I'm going to move to the last part, which is non-commutative geometry. So, so the idea here is that if you go to the Planck scale, then at this point you have that space-time loses completely the kind of notion we have. Geometry does not exist as we know it, and the space-time is completely, I mean, there's no space, there's no time, the whole thing is completely non-commutative. But if I am below but close to the Planck scale, then I can take an almost commutative space, and therefore I can work with that. And of course, the whole gap is how I can go from this almost non-commutative space to the fully non-commutativity of the Planck scale. So this is a kind of bottom-up approach. What I discussed so far, they try to find the theory at the Planck scale. And of course, you might say, well, how can I wake up tomorrow and have a theory that can tell me what's happening at the Planck scale? This approach is a bit less ambitious. In the sense, they say, let us take that data that we have at the electroweak scale, where the LHC works, and we can, from there, try to go up. So it's a bottom-up approach instead of a top-down kind of approach. So, and this approach has also it will also criticize for something at the end, but the beauty here is they try to put together the matter and the gravity. So in other words, what they say is that if I have to build a full theory, a quantum theory of gravity coupled with matter, then the interactions between these two constituents have to be taken from the beginning into account. Whereas in string theory, one is by hand, and in whatever non-perturbative approach I said, the matter content is big. Okay. So then, of course, the idea is to express gravity using the same language as in quantum mechanics. Then, instead of points in a manifold, one has to work with the algebra of coordinate functions. Now, what you have here is that intrinsically, quantum mechanics is not commutative. You have Heisenberg uncertainty principle, so it is not commutative. You have no commutativity of position and momentum. Now, if you consider a classical space and take any kind of information you might have, as an example, I take the phase space, then there is no way that automatically this can be upgraded to a quantum kind of thing. Which means that the quantum algebra of your observables will be some kind of sub-algebra. That means you lose some information, which means you have some fuzziness of your spacetime. So what are the important ingredients here? The important ingredient is that in this approach, actually is the approach that has been put forward by Alain Contes and his collaborators, is to say that I consider at every point, so this plot tries to say that you have a four-dimensional compact Riemannian manifold, and at each point you have an internal space, like a Kaluza-Klein approach. In every point of my space-time, I have an internal non-commutative space which captures the matter fields, the standard model. So then the idea is that if I consider this product space-time and I put gravity in this product space-time, then I get gravity and matter in the four-dimensional space-time. Okay? So in every point of your four-dimensional manifold, you have an internal non-commutative space which captures the standard model. I see you are smiling, I don't know why.
There's music.
There's what?
There's music.
So look, it might sound strange, the whole thing, but I don't know. I mean, I found it myself as a genius idea to try to find a geometrical explanation for the most successful particle physics model we have at hand, which is the standard model. So the approach here, let me finish. The approach here is a different way of studying geometry. how are we used to study geometry? What is the space-time? To find the space-time, what is the space here? I find the distance between you and I. Okay? Now here, the approach is different. The approach to studying geometry is to measure the way that your geometric object is going to vibrate as you bang it. In other words, the idea is, let's say that someone is playing the tambour, whatever, next door, and you do not see, you cannot see, but you can hear the whole tones and the overtones. Can you from there reconstruct the geometry of the space? This is a very beautiful idea that goes back to Weil in, I don't remember when, in 1911. So it really goes a century back. And this goes to the question, can we hear the shape of the drum? So exactly is what I said before. If you do not hear the drum, if you cannot see the drum, but you can hear it, by the fundamental and not the overtones, can you reproduce the geometry? And this already has been shown by Miller in 1964, that if you have Riemannian geometry, you cannot do it. But it has been shown that if you take this spectral kind of background, this kind of tensor product that I discussed before, this kind of, at every point of your space-time, you have an internal kind of non-continuous space that captures the standard model, then you can hear, if you wish, the shape of this spectral pattern. So the dynamics is actually given by the spectral axiom, which is the sum of the eigenvalues of the Dirac operator in this kind of up to a given kind of scale at which you have the validity of your theory. So you can, by doing the spectral axiom approach, find out what is the geometry of your space-time. Yeah, fine. So now, so this, okay. So then the idea here was can I find a kind of purely geometrical explanation for the standard model? So the spectral triple here in this almost commutative space, which is given by, as I said before, by the four-dimensional manifold product with an internal non-commutative space, depends on the choice of the algebra, of the Hilbert space and the Dirac operator. And if you choose appropriately the algebra, you can find the standard model. Now, what I will try to do in the next talk is actually I took this model and I constructed a cosmological framework based on this model. So from the action I took the gravitational sector and I studied which cosmology I can get out of that. So the idea is here that if you take the Riemannian geometry and you put Einstein's theory of general relativity, then you find the standard gravity as we all know. If you take this almost non-commutative kind of spaces and you put the spectral axiom approach, then you can get gravity plus the standard model. And of course the open question which exists, if I have a fully non-commutative geometry, which laws I have to impose, which tools I have to use, and what is the outcome that I am going to get. And this gap is not there. So, okay. So as I said, you consider GR as an effective theory, and then we built a cosmological model based on this non-commutative geometry, and then we're able to test some of their predictions with data. So, which are the criticisms here? Because as you've seen so far, I gave a criticism for everything. So here is this almost commutative space. So you have to see how you can go from the fully kind of geometry at the Planck stage in this kind of almost commutative spaces. Here, so far, everything is classical. Quantum has not entered at all. There have been some kind of attempts in order to encode Azteca variables in this non-commutative spectral action kind of approach and try to build the corresponding of loop quantum gravity based on that. It has not been successful. No, that cannot be done. I think it's a pretty hard problem, so it has not been done. And the last thing that, again, I found it that is a shame, that someone should go beyond that, is this model has been tailored in order to explain the standard model. And one should go beyond that in order to see if you take another algebra, which are the extra particles beyond the standard model that you could have, and what you could extract out of it. So that's, in a nutshell, I think three-quarters of the quantum gravity proposals that exist in the market. So what I will do in the next talk is I will discuss which are the open or unsatisfactory answers that we have in cosmology, and how these attempts, these proposals try to answer these attempts, and then I will tell you why I basically have not a lot of confidence that any of these will give the final answer, and what is lacking, that will be the current stage in this kind of in this kind of approach, and why I believe that at the end of the day, cosmology is probably not the best, but probably the only way that we can dream of testing quantum reality proposals. So thank you.
Thanks. So we have about half an hour for questions. Same setup as yesterday, where I'm going to try to prioritize the students of the program. And so people more senior than me don't take slight at the fact that I ignored you for a while.
So in the overview of the different quantum gravity approaches, you had both string theory and ADS-CFT correspondence. I don't know if you have any views on this, but I was just wondering whether you see them as two different quantum gravity approaches, because you could say that ADS-CFT is just a way of taking the type 2B string theory and representing it in a left and right way.
Yeah, I think I agree with you. I mean, it's just a variation of the same thing. So they could go. One is a development of the other. I mean, it's a further development of the even though that the models that have been built, the cosmological models are a bit different. So the distinction could go there, but otherwise there is the same class.
Right, but quick follow-up. But you also said that the ADS-CFT at least appeared to provide a way for explaining the gravitational degrees of freedom in terms of their quantum origin, and that seems to make for a difference to what we have,
yes,
or at least initially in string theory.
This is true, and also as far as I know, even though they explain that, they can explain the emergence of space-time, they have not been built, quite developed cosmological models on that. So that's the distinction, but yeah.
Yes, so thank you very much. I think Erasmus's question sort of generalizes because of the, I think, 9 or so approaches to quantum gravity that you listed. Even though each one sort of has as its core a different idea, if you want, there are many connections between them, and there, people like Daniela Riti, for instance, use group theoretic methods in a context close to loop quantum gravity, and so on and so forth. So there's many connections like that, and people try to, combine these ideas.
Certainly, I agree with you, because as a matter of fact, group theory is actually derived from loop quantum gravity. The choice of SU2 and all that is to have loop quantum gravity. However, the cosmological models that have been built are different, and I don't like saying that, but it's true. The people are separated, the groups are separated, and there is no common ground of agreement. So there is some common. I mean, tensor modes, group theory, quantum gravity, they go under the same umbrella. But the kind of spin-off cosmological models that have been developed are a bit distinct, even though, as I will show, both LQG and GFT give bouncing solutions and they solve this, but in a different way. I mean, the corrections to Friedman equations are different. So that's why I say that the models are a bit distinct, but the origin of approach is the same. There's a big distinction between string theory, all these non-perturbative approaches, and non-commutative joint. I think these are the three different kinds of separations that exist. And of course, causal sets and all that is even more minimalistic, and therefore goes a bit separate.
Thank you so much for this. This was really helpful to get this kind of overview. I'm just curious, you mentioned for different theories, like different kind of pathologies, and it's sort of, it seems like you have in mind certain conditions of adequacy that we want to expect from a theory of quantum gravity. I'm just curious whether you could sort of like list what the general conditions are.
I'll tell you that actually I probably mentioned it a bit when I said that what I liked in this non-commutative approach is that they said if I want to have a theory of quantum gravity, then I cannot separate the two basic constituents. You see, curvature and matter. In string theory, one is by hand. In LQG, GFT, you name it, the matter content is put by hand completely. I mean, and in non-commutative geometry, this is not. However, the theory remains classical. So I think that a full quantum gravity theory should somehow have an equal footing both the geometry and the matter part. And up to now, you know, each approach is what is the dominant constituent. And I think this is I mean, I don't have a good solution on how you should do that, but I think that this is something that should be seen.
Thank you for this overview. I'm trying to understand this non-commutative.
If you could speak a bit louder, sorry for that,
sure.
but I'm a bit...
No, I just thank you for the overview in the first
you.
place, and I'm trying to understand this non-commutative approach. You mentioned your starting point is an algebra.
Yes,
so I was going to ask what the algebra is,
yeah,
and
the
how you build
algebra,
geometry from it.
yeah, the algebra has been, as I said, tailored in order to give you the standard model. Is an algebra that has a sub-algebra, the SU3, SU2, U1, and also it has also some non-commutativity as a product. So the particular choice of the algebra was taken in order to give the standard model.
And how do you recover geometry from it?
What do you mean by the recovered geometry? So the geometry, then I write the spectral action. So the spectral action is just a functional, which is the trace of the Dirac operator, where you take all eigenvalues of the Dirac operator up to a given value, which is the validity of your theory, which is the scale at which your theory works. So by having this action, then you can find what will be the dynamics of the space.
But at this point, there is no matter.
Yes, the matter is the part that I said that you have a tensor product as your geometry, which is a four-dimensional, a Riemannian manifold for space-time, and at each point you have an internal space-time which encapsulates the standard model. So it's like a Kaluza-Klein kind of approach. Where you have you know, this is a two-dimensional space that you have for the internal space of each point. So it's a particular. So you try to put together like. So the idea is that I take. I mean, this is ad hoc, of course. Is a model. So I take this particular kind of product geometry. And by putting gravity in this product geometry, I find gravity and matter in the four-dimensional space-time. Okay? I don't know how to visualize that better. You see, it's like an internal space at every point.
Just a quick follow-up on that. I think from your answer, the hope would be to put the cosmological constant in the base as opposed to the
Cosmological constant does not enter in this approach.
And the long-term hope would be to put it in.
The long term. I don't know what is the long term. I mean, I cannot tell you because look, this model has been built in order to explain geometrically the standard model. That was the aim. Then what I did is I saw this action, and I said, let me take the gravitational sector of the action, which says higher order derivative terms, and try to build the cosmology out of that. So I try to see what are the Friedmann equations, what are the corresponding. Then I try propagation of gravitational waves in this program, so I take tensor perturbations, and I try to see how I can constrain this kind of three parameters which exist in this expansion of this action. But the origin of this proposal is to explain the standard model, not to do cosmology. So that's why it has been formulated like that. But it has a gravitational sector. Then we try to see how we can test or how we can find some constraints on the three parameters, this kind of expansion of the action. But the cosmological constant, you might say, is another pathological thing does not enter. Inflation does not enter. There are no scalar fields there, so I cannot tell you what else you can do with that. What I would do if I would belong to this more mathematical kind of code is that I would take a different algebra in order to find predictions beyond the standard model, in order to say this is something that can be tested at LHC model my theory. And as far as I know, there has been some little studies around this direction to go to the algebra, but not much. But cosmological constant.
This is going to be a comment question. So I thought that the reason we use the reason for non-commutative geometry is that we have the fund duality between the commutative algebras and topological space.
There is this product space that you take. The internal space is non-commutative. The four-dimensional is the standard kind of Riemannian manifold, fine, but the internal geometry for every point of this manifold is a non-commutative space.
Yeah, but what I was trying to get at is that why we think of it as a geometry that's non-commutative is that in the commutative case, algebras, there's a duality between continuous function and topological space. And then that would be a generalization.
If at each point of your commutative space you have a non-commutativity, then it's non-commutative. The tensor product of the two. Right?
I'm not sure. I think we're not past each other.
I can't hear what he's
I
saying.
think we're just talking past each other. I'm not sure. I'm understanding.
We can discuss more if you want, but probably in a closer distance.
So thank you for a wonderful review. I have two questions. One is, what would you say is the substantial difference between the emergence of particles and fields in the non-commutative approach and the emergence of particles in
It's not a field theory. The non-commutative approach that I discussed is not a field theory. There has been a non-commutative field theory where you have non-commutativity of your, so you have like a commutation relation which depends on this parameter that gives the fuzziness of your space-time, which is a non-commutative field theory. What I discussed here is not a field theory. So I want to make that clear.
And no, I don't know anything, or if you're familiar with this field approach, but I don't know how far this has progressed, but how substantial is the difference between the emergence of the different interactions in this non-commutative approach and the emergence of the different interactions you may find from the vibrations of strings in the string theory approach? What's the substantial difference from this emergence procedure? It's just a matter of a non-perturbative
It's completely different because the interaction or whatever between the strings in the string theory will give you the interactions between the particles. But here it's just a description of the matter fields, the masses, and whatever are the couplings of the standard model. So it does not try to explain. It's much more. It's less ambitious than the string theory says. I'm not sure the string theory encaptures non-commutative loops, yes, but string theory, I'm not sure, so I cannot.
Okay, and just a second short question. When you say that the conjecture in the GFT theory approach
the condensate.
Cosmological, yes, condensate cosmological regimes to emerge from a wide class of models, that when you say that conjecture is not proven, you mean that it's not proven for a general class of models, or that it's not proven for any model?
For any model. This is conjecture. I mean, the only model that has been studied is this SU2 with this tetrahedron and blah, 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 the complex. That has been studied in more, and as far as I know, this is a conjecture. I mean, we had a paper with Daniele where we tried to say that this is good belief to do that, and it is good belief, but I don't think that we have a proof, what I call it is a proof. So it's a conjecture that is very well supported, but as far as I'm concerned, it remains as a conjecture, not as a proof.
And what would be the main reason for the lack of this proof, in your opinion?
Why there's no proof?
Yes.
And I don't think that is very simple to prove it. Nobody did it. I don't know why there is no. I'm not saying that it's impossible to have proof. I'm saying that as far as I know, there is no complete proof of that. It's just a conjecture, which is well motivated, well probably hinted, but now why it does not exist? Ask Daniele to do it. You do your PhD, no?
Yeah, just to follow up on the first question. So, isn't there maybe any way to recover these non-commutative geometry models, even as a point particle limit, maybe of the string theory, or anything like that? Like they're completely separate?
I think it's completely separate. I don't see how you could work with
There's no relation.
I mean, I don't know. I don't know how you can here, for instance, you have this internal space, but otherwise you have a four-dimensional, Riemannian manifold, which is not what is the starting point in string theory. So I don't see how you can work with
Not even like as because in string theory what you usually do, right, is that you basically define some kind of supergravity here, which is just like a field here, and then you can multiply.
But I don't have any supergravity here.
Yes, you need to add maybe super similar.
I don't know how you could. What I said that I can see some kind of connection with mid quantum gravity because there exists this non-commutative. And what I know that there was a group of people in Denmark that they were trying to fight many years back. I'm not going to try to pronounce the name because I mispronounce it, so I will not. They were trying to recapture all these ingredients in the language of spectral dynamics. But this has not been completed, as far as I know, because it's a pretty hard thing to do. It's not that so I don't know any further development, so I have not followed them.
I was interested in this issue with putting things in by hand that you mentioned as your objection to several of the approaches, and whether, so as you presented it, we had in string theory the issue of putting curvature in by hand, and in the other approaches putting all the matter constant in by hand. But I'm wondering if it's a fair comparison in the sense that in string theory we get all the matter constant just from consistency constraints, and we do get the graviton as well, so we have sort of the essential explanation of where curvature comes from. We can imagine having coherent states that might then generate the curvature, whereas in the other approaches it is really by hand that we put these things in, because there's no constraints at all on what kind of matter constant that these models would admit. So it's sort of a very broad question of whether these approaches are really on par with respect to putting things in by hand, or if, as I would think, string theory is in a certain sense better off.
Yeah, I agree that in the other approach the matter content is completely by hand. Whenever I say that, then the proposers of these things say, yeah, it will come from the theory. So there is the same idea that will come from the theory, but I agree with you that it's more brutal, it's completely bad. I mean, actually it's very annoying because you can see I can criticize it because I did it also myself, is that you take this kind of modified evolution operation of your background, and then you put another Hamiltonian completely back one, and then you see, and then you try to see what is the answer to the length. It's a bit, I think that all these corrections should come from the theory itself, but yeah, so they're not at equal footing of criticism in that sense. But my criticism that remains quite severe is the landscape.
Agreed.
So that's.
Yeah, I'm also interested in this issue of introducing things by hand, and I actually would like to ask you to explain maybe in more detail. Sorry?
Yeah, you can.
Okay.
If you stand in front of this thing, yeah, if you stand a little further forwards, you can hear it a bit better.
I was saying that I'm also interested in this issue of introducing things by hand, and I would like to ask you to explain in more detail in what sense in non-commutative geometry matter is not introduced by hand.
It's not
as I understand it now, at the beginning we choose a spacetime, and then at each point we put this internal non-commutative space.
It's not by hand, it's not by, in the sense that I built my model so that there is an interaction between the geometry and the matter, because I construct my geometry so that there is matter at every point of my background. So the construction of the model by itself takes seriously the interaction between these two ingredients.
Okay.
In that sense.
Yeah, my point was that I could have chosen differently either space-time or this internal space. So in this sense, they seem to be independent, but maybe my understanding here is wrong.
I don't know. As I said, this model has been built in order to explain the standard model. If you were chosen it differently, I don't know what you were going to find. I mean, you know, this model has been tailored to give a geometric explanation of the standard model. So then, of course, the question that one asks is, how do I go to this starting point? I should have something which at higher energy scales, which should be more complicated, and somehow I can reduce it to this kind of simple non-commutative space. But you know, is the same thing that starting and saying that loops are the fundamental thing of the structure, or taking causal sets. This is your starting point. I mean.
Okay, so it's
not. Oh, sorry. All these are ad hoc models to some extent, and therefore from this model, how the validity of this model, we'll see the predictions, and you can see if it explains the nature of the universe in which we live. But the starting point is just, you know.
So it's not about the choice of space-time somehow constraining the choice of matter or the other way around, but it's rather about taking from the very beginning into account the interaction of right?
Yeah, I mean, yeah.
So David had a follow-up on that.
Yeah, just following up on the tailored to the standard model aspect, and I'm wondering that there are some loose ends in the standard model, like what the neutrino mass mechanism is, for instance. So does this framework kind of make predictions as to how that ought to work, or is it more that whatever the mechanism for neutrino mass introduction we'd be able to tailor?
Yeah, they did not give any other predictions. They cannot give any other predictions. I mean, that can be tested. The basic predictions that they made was the mass of the Higgs. The mass of the Higgs had the correct order of magnitude, but was not exactly the correct value. And at this point, this approach was criticized a lot. To my mind, completely unfair, because I would I would have less confidence in the model if from the beginning was giving me the correct mass of the Higgs. So usually, you go back by hand. You have a model, you find some prediction, you go to see how you can change how you can a bit, modify the model. So the model now it's successful, but the criticism, if you wish, is yet that doesn't go beyond to make any prediction and being able to test it in a different way. So the model has to be a bit extended to encapture what it has now, but give some extra predictions. And this is the negative thing, I think has been, well, what I say is usually not politically correct, so I will not change now. But this model has been, this is an obsession to give the Higgs mass. So when the Higgs mass was not correct, there was a whole drama in how can you change this. I mean, to my mind, the whole thing would be a bit more loose. Okay, it gives the correct order of magnitude. Let's go beyond that. Let's find some bigger model that gives some prediction. But then the whole story stopped once this obsession of the Higgs mass was confirmed. So from my point of view, I think that we did cosmology as far as we could go. We cannot go beyond unless we make, because it's like, all this model is true at the scale of the theory works. And then you find some of the couplings that depend on the scale, but I do not depends on this coupling. But I cannot run it with time. I don't know how it runs with time. So it's not correct. There have been some studies of people trying to see how these coupling constants are going to change with time by taking the standard and normalization kind of approach, which I don't think that is completely correct. So it's like if my theory holds at the scale lambda. How then it's going to run with a different scale, I don't know. So that's why I don't think that I can go beyond what has been done, and that gives, I think you had another question.
Yes, thanks for this really nice overview. Again, I agree that putting all the pieces together and comparing like this was really useful. And I also thought the talk was a very nice kind of complement to David's talk yesterday. And I kind of maybe wanted to sort of tease that out a bit and sort of make sure people understand how to sort of thinking. Because you said two things that sound on the face of it in quite strong disagreement with things David said. And I think one of them is not really a disagreement, and I want to make sure about that. But I think the other one maybe is more of a disagreement. So the first one was, David gave us a talk about all the empirical predictions of quantum gravity, some of which were cosmological, but more were sort of astrophysical or other kinds of areas. But I take it there's no real disagreement. You said it has to be cosmological, but I take it you're talking about what he called ultraviolet complete quantum gravity, and he was talking about the low energy. So we're in kind of agreement.
Yeah, I go to the ultraviolet. Yeah.
So good. The other thing you said was, I think again this complaint about background dependence of string theory, but I think from the way I understand string theorists to think about this, David kind of gave an argument about why low energy quantum gravity is not background dependent, which is in the sense that, sure, we're doing perturbation theory, so we have to pick a classical solution or pick a vacuum solution and expand about it, right? This is the sort of EFT approach. Mm-hmm. And I think that's the kind of attitude I hear from string theorists as well. Sure, it's perturbation theory, so we have to pick a background to actually expand around. But that's kind of just the sort of formal artifact of the fact we're doing perturbation theory. But we could have picked a different background so it's background independent in that sense.
Yeah, but the results, I think the main difference is what I also said at some point, that in this non-perturbative approach, as I called it, is that you don't do the split. So that's why I call it one background independent and the other not, because you don't split it in background plus a perturbation. So again, I think it's a bit semantics more than anything, no?
I suspect when philosophers hear background dependence, they're sort of really thinking, oh, it's back to Newton and we're putting in this sort of geometry, but it's more kind of a formal point.
Not at all. Yeah. So sorry if there is this confusion with people. So.
Thank you.
You're welcome.
So,
Yeah, I think I'm not sure there even is a disagreement here. I mean, here's I think the disanalogy.
Yeah, well, it sounds like not.
Yeah, here's the disanalogy between. Well, maybe this is a slight disagreement with you, Nick, actually. There's a disanalogy, I think, between what I was calling low energy quantum gravity and at least the traditional situation in string theory. So I was describing how we can do a background perturbation split, but I was doing that subsequent to stating the theory. So the path integral statement of low energy quantum gravity doesn't have that split in it. It's background independent in a fairly full sense. So you can worry about how mathematically ill-defined it is, but formally it's just the path integral and space of all metrics. Now what we don't have in string theory, or at least traditionally haven't had in string theory, is the formulation which stands to those perturbative frameworks as full path integral low energy quantum gravity stands to the background field method in that. Now arguably you can appeal to the conformal field theory dual, and that's partly why string theorists will say that's an unperturbative formulation. But at least in the pre-ADS-CFT way of doing string theory, there's an aspiration to work out what that non-perturbative theory looks like, but there isn't actually a statement of that non-perturbative theory.
Well, that maybe brings us back to Guy's question. I think that was kind of the hope with string field theory, that it would have been something like that, right?
But I think there are two papers from like the early 90s by Witten, Zubak, Zen, developing a framework for both open and closed string field theory, where everything would be background independent. It's true that the framework has been stuck, I guess, over the years, but in principle the formulation is there. It's just it's very technical and very complicated.
And then that would be the kind of
right. Yes, but I think it would be. I mean, I take it you wouldn't want to say that we can be securely confident that string field theory is the thing that we can use as an unperturbative formulation of string theory. It's a proposal for that, but I don't have the sense that string theorists would universally agree that yes, absolutely, that's the correct and unperturbative formulation of string theory. Correct me on that.
It's out of my expertise to reply to that.
I mean, I think at points I've looked on the archive for sort of, the frequency with which the term string field theory gets. So right in the early mid-90s, there were lots of papers, but it's very much fewer now. So
but then
you say it's about right.
But this can just be a hype, right? Because after ADS-CFT, then.
Yeah. Maybe it'll come back.
To some extent,
this is a sociological statement.
So in some sense, field theory is supposed to stand to string theory as modern QFT is supposed to stand to relativistic particle mechanics. But of course, in full QFT, we've got an absolute abundance of things we can do with the full QFT machinery that we just can't capture in non-relativistic quantum mechanics. And my sense is we don't have that fecundity of application of the string field theory.
So we are at time. I will give our speaker the opportunity to left for a final word, but otherwise.
Well, I think we all agree with
All right.